In this course, you will create an app using your phone called Blynk and use it to control your motor, just like I'm doing here. We'll be able to start the motor and run it in each direction, left and then right, just as you see here. You'll also be able to adjust the speed and other settings on the fly. Just like I'm doing here, I'm decreasing the speed by 10 times. And we're going to start the motor up one more time. And finally, you'll learn about a feature called Stall Guard that will allow us to stop the motor at any time, just like that.
So in the app, if we go ahead and hit set 0, this zeroes out of position. We can then move, as you can see right here, to any location that we want. We can move it 72%, 28%, and it just always moves to the direction that we set. If we want to reverse that, we can hit the reverse motor, and that will pretty much reverse the direction that it spins in order to get to these percents. We can then update the inches, so we can say 1 inch or 1.25, and let's go ahead and zero that out. And if I were to open it up to 100%, you can see the motor just spins to 1.25 inches. We can then accelerate to different speeds and set our velocities. We can set the current to open and then current close, and find the set stall value close and stall value open.
So now we're going to tie it all together. I'm going to go line by line in the Arduino code, and we're going to go over every part of the sketch and go over everything we just learned. And if you haven't learned anything yet, please go back through the course, go back through each section, and make sure you understand all of these parts in case anything is confusing. So we begin by including Arduino.h. This is just required for all Arduino sketches. Then we include ExcelStepper.h, TMCStepper.h, and Preferences.h. These are just required libraries that we need in order to continue. Then we set up the pins. Step pin will be on 13, direction pin 14, and so on. These are all related to the Val 1000 board. If you have something different, please go and update the pins that you do have. Next, we create objects. We create the Excel Stepper object. We call it Stepper. We then assign the correct enumerator. In this case, it is driver. The reason it's driver is because we have a stepper driver that we're using and a direction pin and a step pin. We then input the step pin and then we input the direction pin. Then we create the TMC stepper object, which we then call driver2. We then assign the serial port that we're using. In this case, we want to use serial 2 because serial 1 is being used by Arduino for the serial monitor. So since the ESP32 has 3 different serials, we're going to go ahead and use serial 2. Then we put in the RS value. In this case, it is 0.15. Sometimes it might be 0.1, 0.12. It really depends on the board that you're using. So please look at the current sense resistors on your board. If you don't understand what the current sense resistors are, go ahead and review the section on current sense resistors. And then we put in 0. And this is just a slave address. Since we don't use that, we just leave that at 0. Then we go ahead and set up the dual core object. Here we're going to call it C0. And finally, we set up the preferences by calling it preferences local. We then include our other header files. As you can see up here, all the other ones that we have, we just include those. Now we want to set up the function that triggers the stall guard. So as you remember, stall guard drives one of our pins high. As soon as that pin is driven high, we want to trigger this function. Then we place IRAM to make sure that it gets saved into a special section in the ESP32, so it's called really quickly. As soon as this is triggered, we want to decelerate, which is the same thing as accelerate, but we want to decelerate extremely fast, and we want the motor to stop moving in its current position. This is just a kind of a fancy way of saying stop exactly where you are right now. We're going to skip over these sections. You can set these up if you want. These are for the limit switches if you'd like to put 2 limit switches on your Val 1000. Then we begin the setup, say serial.begin. This is just for the serial monitor. We then begin the preferences library. Again, we called it preferences local.begin. Then we give it a name. It doesn't really matter what it is. Here we call it local, and we set this to false. Then we go ahead and load all of our preferences by executing this function load preferences, which is saved in the preferences.h. So we go to preferences.h, and we can see right here, this is the load preferences. We then go ahead and load all our variables just in case there's a power outage. We got to reset. So we set stall close is equal to preferences local dot get int. We then look for the stall close key, which should then load the correct value. And if that doesn't exist, it's going to go ahead and load the 30 right there. We then move on and just do some standard pin mode setups, which are required by Arduino. We want to set the enable pin, output, direction pin is output, and so on. So kind of standard Arduino stuff there. Then we move on and we disable the core 0 watchdog timer. The reason we do this is just it's not reliable like we learned about earlier. And here we go, and next we're going to set up the core. So this is setting up the core 0, and we want it to run this core 0 assignments, which we will go to in a little bit. Next, we want to set up the interrupt. So you remember we created the function for the interrupt. If we want to go back up here, it's right here, stall position, that's the interrupt. And in the setup, we actually want to attach it. So we create this attach interrupts, stall guard, which is just the pin that we have stall guard on, which in the Val 1000 is pin 2. And then we put the function that we want to call. So in this case, we're going to call the stalled position function. And we want to look out for the rising edge, just because we're going from ground to our 3.3 volts. And we're just looking for the rising edge once the voltage is rising. Next, we're going to do some basic driver setup. And right now we want to send some UART data over to the 2209. First, we want to initialize the serial port 2 on the ESP32. Then we want to enable the UART on the TMC2209. We set that to true. And then here we begin sending the data. The following here are just required. You can always reference the data sheet to learn more about what they do, but we're not going to touch these or change them. We can always change the motor microsteps in a different section, but we will not change it here. And finally, if you want to enable spread cycle or stealth chop, that's where we do it here. In this case, we want it to be really quiet, and so that's why we're using stealth chop by setting spread cycle to false. We then set up the Excel stepper library. We set up the set enable pin, and we place that on the enable pin, which is the macro that we have up here. In this case, the enable pin is 27. Again, change that to what you have if you don't have the Val 1000. We then set up the pins so that they're correctly saying high or low for this enable pin. We set the current position to X actual, and we disable the outputs to make sure that the TMC2209 is not enabled. Finally, we update the shaft direction to make sure that it's spinning in the correct direction. Then we go into our loop. These are our motor functions only. We're going to put our Wi-Fi functions in a different loop. So we first set up our 2 buttons. We have 1 button here and 1 button there. If we have a digital read on button 1, then we set the stepper move to all the way to max steps. This just makes it open to 100%, and we set the command to move. Else, if we have button 2, we then set the stepper move to 0, which is closing it, and we set the command to move as well. Next, we're always on the lookout whether command equals stop or command equals move. In the case above, once we change the buttons, we get command equals move, and that just initiates the motor control function called move motor, which we will go to in a second. Finally, we have our Wi-Fi core, and remember we set up the core 0 assignments. We set this core up in the setup right here, and we disabled the watchdog timer for this core. And in this core, we begin with a Blynk statement here. We need to do blynk.begin, and that just initializes our connection. It takes your authentication token, your ID, password, and it establishes the connection. And then we have this for loop that will pretty much run forever, and it just calls blynk.run, which keeps the connection open and alive with the Blynk server. So next, let's go ahead and look at our motor control.h and see what's going on here. We begin by setting move to position variable to stepper.target position, which is when we set stepper.move to, this is just the value that is stored in the stepper.move to. Then we set the x actual to the current position because we always want to know exactly where the motor is at. Next, we enable the outputs, which is just the enable pin, so we're turning on the motor driver. We set the acceleration to our moveAccel variable. We then set the top speed to our move velocity variable, which holds our speed. And then we set the t equals threshold, which is related to our top speed. And remember, this is our stall guard threshold on when it turns on after a certain velocity has been reached. Then we check if move to position is greater than x actual or if move to position is less than x actual. This way we can load our different values. If it is greater, then we're going to go ahead and load our current open, and then our stall open. And the reason we do that, again, is because our stall is directly tied to our current. So if we change our current, we also want to change our stall value. And finally, we call stepper.run in this loop, which just says, while the current position does not equal the target position, keep calling stepper.run. Once the current position equals the target position, we then stop this and move on. Then we change our x actual to our stepper.current position, and we save this in our preferences library by calling preferences local.putInt, and we call our key value pair, we call it x actual, and we save our x actual value into this actual key. Finally, we call stepper.disable outputs, and this disables the stepper board so that we save energy when it's not in use. And finally, we do a Blynk update equals true. And the reason that we do this, let's take a quick look back on the main page. Once Blynk update equals true, we call a simple blynk.virtualWrite v2. And what this does is it sets our slider and it updates the slider to the current position that the board is actually at. And we turn this off to not keep calling this command. Next, let's take a look at our blynk.h header file to see all our Blynk commands. First, we include all of the following, which are just required to establish a Wi-Fi connection. Next, we update our authentication token. So be sure to place the authentication token that you received from Blynk in this area, and be sure to leave it in quotes just like this. Next, you put in your Wi-Fi ID right here. That's just your Wi-Fi name. And you put in your Wi-Fi password in this area. We then add the Blynk timer if you ever want to use the Blynk timer. Then we add in Blynk connected, which runs as soon as your board connects to the Blynk server. Once a connection is established, we call the blynk.syncAll command. What this does is it syncs the values from the server and updates the values on your board. Just in case you decided to update values on your board when there was not a connection. This way, everything is always synchronized with the Blynk server values. So we're not actually going to use this one, but if you want, you can go ahead and put this into Blynk. This is a segmented switch, and you place it on V1. This allows you to do up to 3 different things. You can either set it to close, which then sets your move to all the way to 0, which closes it and initiates the command. Or it sets it to max steps, and that opens it up to 100%, or it sets it to stop, which then calls the stop command and stops your motor where it is. However, we're not using it, but you can if you want. So next, we set up the position slider. We wait for a value of 0 to 100 to appear. We then take the max steps, divide that max steps by 100, and multiply it by the number that appears. This then sends the exact amount of steps to the motor to move to the correct position. We then put stepper.move2, which is Q, which again was this right here, and we initiate the command to move in order to start that process. On V22, we want to set the max distance. So what we do is we say param as float, which is the value that we get from Blynk, and we multiply it by 1 inch. This gives us the exact amount of steps in order to move the inches that we want from the app. We then convert the max steps into an integer and save that max steps as an integer because positions can't be floats. So we want to make sure that the positions stay as integers because they are whole numbers. Next, we set the acceleration to V21. We take the number that comes in from Blynk and we multiply it by 10. The reason for this is that Blynk can only go up to 9,999, but our acceleration value is much higher than that. So we take the value in Blynk and we multiply it by 10 because that's the value that we need to put into the library here. So then we set our moveAccel to Q, which is what we have here, and we save that into our preferences. And finally, we set the stepper.setAcceleration to that value. We then go to V34 and set acceleration and do pretty much the same thing. We set the param as int, which is the value that we get from Blynk, multiply it by 10. We then turn the move velocity variable into that number, and again, save that into our preferences and set stepper.maxSpeed to this move velocity. Then we go ahead and change the tcools value, which is the stall guard threshold to activate stall guard, and this number is directly related to the velocity. We then use this power regression formula that I have created in order to create the tcools value based on the move velocity, which we just did above, and we go ahead and do a blink.virtualWrite and update the value in the Blynk app to this new tcools, which we just calculated. Next, we set up our stall guard values. We can use a value of 0 to 255. I do this just in case Blynk sends a value that's larger than 255 or less than 0. This way it sets anything less than 0 to 0, and it sets anything larger than 255 to 255. Then we set our stall open variable to Q, which is the value that came in here, and we save that into our preferences. Then we come to V25, which sets our current open value. We set our int Q to the param int, which is the value that comes from the app. We then save that value in our preferences and set our driver2.rms current, which then transmits that current over to the Trinamic driver. We then do the same thing for V26 to set the current close value. V36, we set the reverse motor. So if your wires are flipped and it's not moving in the correct direction when you hit the open or the close button, you just go ahead and set this. And what that does is it just sets the close position to either 1 or 2, which you might remember is what is being set in the settings. So if we go back to the settings really quickly, we can set close position equals 1, do this, or false, and it's pretty much setting that close position equals 1 or 2, and then it's setting the driver2.shaft to false, and again that's sending a UART signal, UART datagram over to the TMC2209 and setting that shaft, setting those bits to either true or false in order to get the shaft to turn the correct direction. And then of course we go ahead and save that into our close position preferences library. Then we come down to V50, which sets our 0. This is really important. If you want to set your position to 0, you go ahead and hit the V50. Basically, remember, our positioning always starts at 0 and then it goes up to 5,000. So we always need a 0 position. So if you move your motor and you want to reset that 0, you press that V50 and that sets your x-actual to 0. And on the stepper, it sets the set current position to 0 and then updates that in the preferences, and then finally does a blink right and changes the slider. So let's say that your slider was maybe at 31% As soon as you hit the V50, it'll change that slider to 0. And then finally, we have our V125, which allows us to set our T-cools value. You might remember that we did this earlier. We went up here to the velocity. So when the velocity changes, this T-cools automatically changes right here. But if it's not working out for you, you can always come over to V125 and then manually update that T-cools value. Finally, let's take a look at our variables. This just contains all the random variables that we're using. One of the most important sections is actually right over here, and this sets our steps per revolution. So if you're using a geared stepper motor, we're going to change this to that ratio. We're going to then update the diameter of our pulley and then set our microsteps right over here. Then these, don't worry about those. Those will automatically update, and it kind of does the math to convert from diameter into circumference. And then finally, we get our 1-inch value by the system automatically doing some more math for us. And this 1-inch value is then used throughout the sketch in order to move our device 1 inch or 12 inches or whatever amount at a time.